For the next section, we're going to look at combining work and energy. Now, in the textbook, this links with page 72 and the questions start on page 75. So, there are two main ideas that we're going to look at in this section. The first is the principle of conservation of mechanical energy. And as it says there, the idea being that assuming there's no external forces other than gravity acting, the sum of the gravitational potential and kinetic energy remains constant. So as long as we don't put any work in or take any work out of the system, the total energy is going to remain constant. Linking to that is the work energy principle. Now, what this is saying is that if there is a change in the total energy, this is going to equal the work that's being done. Now, this could come in two different forms. We could either have energy being put into the system or energy being removed from the system. Now, I like to sort of combine these and think of them all in one go. It's how I've always thought through it. And I like to think of it as this. The initial energy, which is a combination of kinetic and potential, plus any work that's put into the system, is going to equal the final energy plus any work that comes out of the system. So work in might be a car engine or someone riding a bike putting force into the system, which is going to increase the amount of energy, hence putting it on the initial side. So that's the total amount of energy we possibly have. Then the other side, obviously any gravitational potential or kinetic energy left over, plus any work that's come out of it. So wasted energy, for example, friction is a very common one. Now, to begin with, the situations we're going to look at, we're not putting any work in, so that bit's going to be gone. We've just got an initial energy, and then we're occasionally going to have some work coming out of the system, as I say, such as friction. So let's go straight to an example to see this in use. So here we have a stone being dropped into a pond from a height of 3 meters. We're going to use conservation of mechanical energy to find the speed with which it hits the water. So, as always, start with a diagram. Here's my stone. Here's my pond. This has a mass of 1.5 kilograms. And we have a height here of 3 meters. Now, one of the really important things on these questions is always define your zero potential energy. Now, as this is my highest point and this is my lowest point, this is where I'm going to take zero potential energy from. So whenever I'm measuring my gravitational potential energy, that is where it is zero. So now I'm going to look at the equation I talked about. I want to look at, there's no work being done, the only force is gravity, so my initial energy equals my final energy. So, initial energy, we're above our zero potential energy, so we have some gravitational potential energy, mgh1. We aren't moving, we're stationary to begin with, so I'm not going to include any kinetic energy there. And that is going to equal, at the other side, when we hit the pond here, we're now at our zero potential energy state, so we have no gravitational potential energy. We do, however, have kinetic energy, so we're going to have half mv squared. Now it's just a case of substituting in and solving. So we have 1.5 times 9.8 times 3 equals a half times 1.5 v squared. Now working this through, we get 44.1 is equal to 0.75 v squared. So 58.8 equals V squared. So V equals 7.6681, which we will round to V equals 7.67 meters per second to 3 significant figures. And we're done. For this second example, I'm going to introduce a slope as well. And this time we've got some friction, so we've got some work going on here. Now, let's start with the diagram again. So this time we've got a slope at 30 degrees. Now it says the particle moves, I know this is steeper than 30, but it's only a diagram. The particle moves 3 meters down the slope, and we're at an angle of 30 degrees. Okay, the particle has a mass of 0.7 kilograms. Now, as always, start off by defining our zero potential energy. So this line here is my zero potential energy marker. Now, because we've got a change in height, it's a good idea to work that change in height out early. So if I look down here, this change in height, we've got a nice right angle triangle, a 30-degree angle, because it's the same as that, a hypotenuse of 3 meters. So whichever way you'd like to work it out, let's do it the old-fashioned way. Sine 30 equals, let's call that h over 3. So we should remember sine 30 is 0.5, so h is equal to 1.5 meters. So I'll put that on my diagram. Okay, now we've got no work being put into this system. There's no reference to any work going in. We do have some friction, so there is work being done. So let's set up our equation again so we can work through this. So our initial energy at the start, we have no velocity because it's released from rest. So we have mgh is all that we've got going in. At the other end, our final, we've got no potential energy because that's where we defined it. We are going to be moving. We've got a final velocity of 4.5. It was given in the question, 4.5 meters per second. So we've got half mv squared. And we've also got some work done, which we're just going to call work done for now. We'll deal more with it later. Again, at this stage, it's just plugging in some values. So we've got 0.7 times 9.8 times 1.5 is equal to half times 0.7 times 4.5 squared plus work done. And then follow that through. So 10.29 equals 7.0875 plus work done, and that gives us 3.2025 equals work done. Okay, now the question, if we refer back to it for a second, asked us to calculate the magnitude of the friction. So it wasn't the work done against friction, we actually want to know the size of the force. So this is where we need to draw in some of our other knowledge, and we should remember that work done is equal to force times distance. Okay, now the question told us we went 3 meters down the slope, so our work done, 3.2025, is equal to our force times by 3 meters. By dividing through by there, we get our frictional force is equal to 1.0675, which again rounds to 1.07 newtons And that's again to three significant figures. Second example done.